So let's focus on costing equipment and cost of equipment and cost indexes. So to estimate the purchase equipment cost, there's different ways to do this, right? The best way to do it is actually ask for a quote from a vendor, right? If you can do that, just do it. It's the most accurate way to get the equipment cost from the manufacturer based on a specific information for that equipment. Requires significant engineering at that stage if you want to know exactly the quote, right, and the cost for that equipment. The thing is that when we're doing preliminary economic analysis, like the one that you're doing in this class, you may not know the details about all the specifications of the equipment, because typically when you do your design as a chemical engineer is that you send your equipment design to another type of engineer, like for example a mechanical engineer, an electrical engineer, and together you actually design the equipment. If the equipment is something that is available in the market already and doesn't need to be customized, well, that may be a little bit simpler, but you always need another engineer to corroborate that. So for us may not be suitable because we are typically designing things from scratch and we don't know exactly yet what is the final design for the equipment. Also, you can use previous costs on similar equipment and scale for time and size. This is reasonable, accurate. Be aware, right, of large extrapolations in foreign currencies. If you're doing currency exchange, it's not the same thing as using pounds from England or pesos from Mexico, depending on where you're purchasing this. So make sure that you have like a conversion rate between the currencies. Also, the cost estimating charts and scale for time. These are typically less accurate, but they're pretty convenient, okay? So for us, we may have, depending on the statement, on the analysis that we're doing, we may have the second option, or we may need to estimate it using the third option. I think the most important thing is that you remember here is that for the type of estimation that we're doing, we need to take into consideration two things that can affect the estimation of the purchasing cost: the capacity or the size of the equipment and the year that we're comparing, right? It's not the same thing comparing something in 2000 than 2019 because the inflation is different and the calculated cost will be estimated differently. So let's get into that. So for the first effect, right, the capacity on the purchased equipment cost, this is the CP, right? Basically, what we can do is use a simple relationship between the purchase cost of and an attribute of the equipment related to units of capacity. And this can be related, right, by comparing the cost of the equipment that you need the capacity for compared to the cost of the equipment that you know information of already. And using this relationship, right, you have the attribute capacity, you have the equipment attribute that can be the capacity list, and I call it A, and it's an attribute because it depends on the equipment. Like the capacity of the attribute for a heat exchangers is the surface area of the heat exchanger, but for a vessel is the volume. So this is what we call it A, the attribute. Please do not confuse this with the area. Not necessarily we're all calculating areas. If you're looking to a pump or compressor, you're probably using the horsepowers or the shaft work, or depending on the equipment, right, will be the type of attribute. But basically this is it, right? And the important thing is that you don't forget that there is a cost exponent related to that. So heat exchangers, vessels, all of this equipment have different relationships between this cost from different capacities. They're not linear. So this is just to show you exactly that. Here on the left side, you have a table with the cost exponents for selected process equipment. So on the left side, you have different equipment like a compressor, a heat exchanger, a vertical tank, centrifugal blower, jacket kettle, glass line. Here on the center, you have units of capacity, and this is what I'm saying. The attribute of that units of capacities is different. For compressors, we're looking at kilowatts. For exchangers, we're using an area. For tanks, we're using volume. For centrifugal blower, we're using the standard meter cube per second. And here in the jacket cattle glass line is also the volume. So for each of those, we may find in the literature the cost exponents. Sometimes you may get this from the Paris. For example, this table is from the Paris. And notice that this equation, right, which is an equation, has a correlation, right? So this is where I mentioned before that you have to be aware of large extrapolation, because if you have a correlation that is defined, that exponent is for that correlation. If you're estimating things under or above that particular correlation boundaries, you may be having issues, right, with your calculation. So may not be as accurate as you are thinking. So notice that if you do a cost variation of the exponent based on the different type of equipment, we notice from the literature that, or this analysis, right, even from the Paris, that they report that most of the equipment lied, right, that a good estimate for the equipment, that when you don't know the exponent, is to assume that the exponent is 0.6. Always the best way is to use the cost exponent for that equipment if you can determine by data that you have from previous equipments or information from the manufacturer, something like that. But in case you don't have the cost exponent, you can feel comfortable, right, by using the 0.6 as the cost exponent. So once again, you can also represent the same equation, but using graphs. So you can have an equation like this with data, right, to calculate using the equation, which is just obeying a linear behavior, right? Basically, that's what you're doing. Or you can actually see, capacity cost plots like the ones that you see on the right side, that instead of giving you the equation, right, basically while you're calculating the slope, and the slope tells you the unit cost, right? Here will be the cost per unit, It will be the purchase cost per dollars, right, of the equipment that you need over the capacity, right, of that to the end. So anyways, this is graphs that you can get, right, to do this. You can use the equation, you can use the graph. There's multiple ways that you can estimate this. So either it depends on the information that you have available that you're going to be able to use this. So here on the right side, I probably will get, right, you have the gallons here. Notice things about this graph is that it is in the log form. So you may have log form access, or you may have log linear form. Please be careful while reading this, okay? So here you have in the 10 to the 3 gallons. This is the capacity for this equipment. Also notice that corresponds to a unit cost, right? That can be related here. And that factor you can use to calculate your particular cost for the desired equipment. The other thing that I want you to notice is that you have here 4 different lines. So all of them are tanks, but I want you to notice that depending on the type of tank, so here you have 2 mixing tanks, and the mixing tanks are more expensive than the storage tanks. And if you have a materials of construction that is carbon steel, like I mentioned before, carbon steel is the base materials of construction, then it's going to be cheaper than using a stainless steel. So it's not only the type of tank of equipment, right, the right use, but also the materials of construction. Stainless steel may be good for operations where you have high temperatures, when you have chemicals that are not compatible with carbon steel. However, it has a cost penalty as shown here in this graph. And we're going to get into that, but I just want you to see it here. The other thing that I want you to notice is that the information, this equation that you're using, right, is stamped for a particular date in time. So you always have this type of graphs stamped for a time. So you may be able to find the correlation with capacity, but you're still comparing the capacity for 1985. So there, we need to find a way, right, to extrapolate that, for example, for 2019 or 2020 or 2021, depending on when you want to calculate this for. So in summary, right, we have that the typical values for n lies between 0.4 and 0.8. So we can often use, if we don't have the exponent, capacity exponent, or if we don't have data to be able to calculate that, then what we can assume often is to use the 0.6 as the exponent, and this is referred as the 6/10 rule. It assumes all equipment have n equals to 0.6 in a process unit and scale up using this method for whole processes. It is just an order of magnitude estimate. If you need to do this, like the final economic analysis, you really need to get better information. But for this class, we can use any of this method, right, to get the purchasing cost of the right equipment at the right capacity. This is an example, right? A new plant order a set of floating head heat exchangers. This is the area and the cost for that particular equipment. What will be the cost for a heat exchangers for a similar service, right? If we have that the area of that new equipment is 50 meter square and the exponent, right, for that type of heat exchanger is 0.44. So what we do, right, we have the equation for the capacity, relating the capacity. We can calculate the cost of our required equipment, right, by multiplying the cost of the equipment that we know the price for. And here we have the area of the attribute, right, of the equipment that we want to get the cost for, which is A here. And divided by the attribute, right, capacity of the equipment that we know the price for, everything elevated for the 0.44. We can use 0.44 because we have that information. You may have equipments that have, you have information about other two type of equipments, and that would allow you to calculate the 0.44, the n, right, which is the exponent, and that can be used to calculate other areas. So that can be really useful if you're doing estimates in a small project, even in your plan. Having this concept is really important because you just need to get the right information from the company. Maybe your company has the same equipment type, the same materials at the same year, right? And then you can just get the n, right, the 0.44 in this case, or the exponent, and that would allow you to calculate better the other one. If you don't have the data though, you can then assume that the exponent is 0.6, okay, which is the 1/10 rule. So it's pretty straightforward, just playing with the information that you have. So notice here a big important term that is called the economy of scale. The larger the equipment, the lower the cost of equipment per unit of capacity. And this is true under a certain point. If you cannot ship that equipment by regular means and it has to be customized because it's too large, therefore you may need to pay extra. So it is true, the economy of scale, until a certain limit.